Hi everyone, I hope you're okay, and I really hope that guys the videos are helping you out. This is video number 2 guys, from the 11 videos whereby I'll be answering past question papers with regards to momentum and impulse. Please note that guys there's a full playlist there on the description below. Just click the second link, it will direct you straight to that playlist, and the first link, that's where I'm teaching momentum and impulse from scratch. Based on your understanding, if you still want to learn, please click the first link, and if you do have the knowledge but now you want to apply it by answering past question papers, just click on the second link and then answer the questions with me. And most importantly guys, please don't forget to share this video to your peers. Don't forget to like the video if you're getting helped, and do ask questions on the comment section. Most importantly guys, please help us grow the channel by just subscribing. Okay, question 2. We are told that the diagram below shows a bullet of mass 20 grams that is traveling horizontally. The bullet strikes a stationary 7 kg block and becomes embedded in it. The bullet and block travel together on a rough horizontal surface for a distance of 2 meters before coming to a stop. Okay. We can call the bullet object A, and then the block we can say it's object B. So the bullet will travel from rest, and then it will come to a stop after traveling for 2 meters. So if we call this point X, not X rather, let's say it's point P and Q. The velocity at point Q will be 0 meters per second. Now I'm talking about the bullet block system, right? It will travel from here up until there. Are we together? So the bullet block system, after traveling 2 meters, it will come to a stop, and hence the velocity is 0 meters per second. We don't know the initial velocity just after the collision. Are we together? But in question 4.1, we are told to use work energy theorem to calculate the magnitude of the velocity of the bullet block system immediately after the bullet strikes the block, given that the frictional force between the block and the surface is just 10 newtons. Okay, if one would draw a free body diagram of the bullet block system after the bullet strikes the block, you'd find that yes, the bullet block system is on top of a surface, hence we have a normal force. Right, together, and then the bullet and the block are on the universe, so they have to experience a gravitational force. However, there's a frictional force which opposes the motion. Frictional force which opposes the motion. There's no any other force that pushes the bullet block system towards the right. Right, together. So we have only one horizontal force in here. Are together, and that horizontal force opposes the motion. So if we're going to use the work energy theorem to calculate the magnitude of the velocity of the bullet block system immediately after collision, we're just going to say work net is equal to the change in kinetic energy. Remember that the work energy theorem states that the net work done on an object is equals to its change in kinetic energy. Okay, but remember that guys, a work is the product of a force and displacement in the direction of the force. Are you together? So whatever force on question, if I wanted to find work done by normal force, that means I was supposed to use normal force there. Right, together. So if I wanted to find the work done by gravity, I was supposed to use work done by gravity. So since I have a work net, if I want to find the work net, that means I'm supposed to use the F net over there. All right, together. So now I know that work net is equals to F net delta X cos of theta, and then change in kinetic energy is just half mv squared final minus half mv squared initial. Okay, there's only one force which is acting here, right, together, which is just a frictional force. I'm going to write the magnitude of it. The distance that it traveled, it has traveled a distance of 2 meters. The cos theta here, guys, go work energy in power, ne? Work is equals to F. This theta over here represents the space between the force in question and the direction of motion. We can see that the block and bullet system are moving towards the right. However, frictional force, let me indicate in blue, frictional force is acting opposite to it. So the angle between the direction of motion and the force in question is 180 degrees. 180 degrees. So this is equal to half. When the bullet and the block are combined together, their total mass is 7 kg plus. Remember that in physical science you always change the grams into kilograms, right? You'll obviously divide the 20 by 1,000. You'll simply get to 0.02, and then the total mass is just 7.02 kilograms. 7.02 kilograms. So we'll just substitute 7.02. The final velocity of the bullet block system, it is 0 meters per second. Why? Because it will eventually come to a stop. I have 0 meters per second, 1 over 2, 7.02. I'm just looking for the initial velocity because I don't know the velocities of the bullet block system at position P. On the left hand side, I will simply have negative 36, and then this will give me 0 minus 3.51 VI squared. Let me confirm. 7.02 multiplied by half, yeah, it's 3.510 squared, ne? And then obviously VI squared is just equals to, no, let me just write to VI. VI is equals to the square root of negative 36 all over negative 3.51. What do I get? The square root of negative 36 all over negative 3.51. The speed of the bullet, the magnitude of the velocity of the bullet block system just after collision will simply get to 3.2 meters per second. So now I do know that the velocity of the bullet block system immediately after collision, it was 3.2 meters per second to the right. Okay. Okay, then now the second question, they want us to state the principle of conservation of momentum in words. It simply states that in an isolated system, the total linear momentum is conserved in both magnitude and direction. Okay. And then now they want us to calculate the magnitude of the velocity with which the bullet hits the block. So obviously, after stating the conservation of linear momentum, guys, we have to use it all together, because this is an isolated system. There are no non-conservative forces, and when the block is standing, it does not experience kinetic friction. So it's an isolated system all together. So since we have an isolated system, I can simply conclude that momentum is conserved by saying the sum of the momentas initially is equal to the sum of the momentas after collision. All together, and by definition, momentum is the product of mass and velocity. So it will be the mass of object A multiplied by the velocity of object A initially plus the mass of object B multiplied by the velocity of object B initially. And then after collision, both objects A and B, they move as one unit. So just going to say mass of object A plus the mass of object B multiplied by their velocity. Okay, I do know that the mass of object A is just 0.02. I don't know the initial velocity. The mass was 7, but it was resting, it was stationary. And then I have 0.02 plus 7 multiplied by 3.2. And then I'll simply have, therefore the velocity of the bullet just before collision, let me calculate. I have 7.02 multiplied by 3.2 divided by 0.02. Speed is single. Okay, I still get 1123.2 meters per second. So the bullet was traveling at a speed of 1123.2 meters per second. So that's how, guys, we're supposed to tackle this question. Please note that, guys, these are questions from final exams, so they are assuming that you have learned the entire content altogether. This part was work energy and power, and then the last two parts, it's just momentum and impulse. So they included this because final exam you would have learned everything altogether. So yeah, guys, just stay tuned and wait for more videos. Thank you.